Okay, everyone, welcome to the morning session. Despite the rain, thank you for coming. Today, our first talk is by Professor Haizhong Li from Tsinghua University. Professor Li will speak on summation for two sets in hyperbolic space.
Okay. Okay. Thank you, Professor Miao, for introduction. So thanks for scientific committee of a second International Congress of Basic Science giving me this chance to report my results with my former student. Today I will talk the summation for two sets in hyperbolic space. We will talk about the result we developed for the hyperbolic space. So my talk will divide in the four sections. The first section, we will talk hyperbolic space and holistically convex domain. And the second section, we will talk about the hyperbolic summation. This concept we first introduced. So as we know, in the Euclidean space, given two domains, we can define the linear summation for the two domains. But for hyperbolic space, because the law linearity, so as more than 100 years, people cannot introduce the concept of the summation. So the second section, we will give the our definition. So the third section, by use our concept of hyperbolic summation, we will introduce we call the holistic Brunn-Minkowski theory, especially for the given prescribed measure problem. We will introduce the Brunn-Minkowski problem. So the last section, we will talk about the geometric inequality for the convex domain and the whole convex domain for on the hyperbolic space. Let's begin with the section 1. So hyperbolic space, we write down the Hm plus 1 is a simply collected Riemann manifold with a constant negative curvature minus 1. So below this unit sphere is a simply collected Riemann manifold with a constant curvature 1. But hyperbolic space is a constant negative curvature minus 1. So there are several models. But in my talk, we will talk about the hyperbolic model and the Pangana disk model. So we don't talk about the half space model and the Klein model. So first we talk hyperbolic model. Hyperboloid model is considered a hyperbolic space realized as space-like hypersurface in Minkowski space. Minkowski space, as we know, is the n plus 2 flat space with a Lorentz metric. Metric is inner product x equal to x1 square plus x2 square and minus n xn plus 2 square. One sign is minus, so we call it Minkowski space. Consider the space-like hypersurface hyperbolic model as a pseudosphere. Hm plus 1 is defined by the length of the, in this metric, with minus 1. As a picture I draw, the two component is upper component and the down component. So because two component symmetry, we just consider one component. So here we consider the hyperbolic model with the last component is positive. So hyperbolic space as a pseudo sphere in Minkowski space with the last component is positive. So this is hyperbolic model. So use this model, the advantage is we can have the geometry induced from Minkowski space. So for the analysis to study the geometry of hyperbolic space, we also have the warped product structure. Means the metric of the hyperbolic space can write down equal to dr square plus sinh r square times kinetic metric of the unit sphere. So here, as there's some picture, give one position vector x, we can make the projection to the Euclidean space sinh r theta. Theta belongs to unit sphere. So here is the picture, give some connection between the point hyperbolic space with the point on the Euclidean space. So the most important model is the Pangala disk model. So in fact, the Pangala disk model, it can be derived with the use stereoscopic projection of the hyperbolic model on the unit disk. We consider disk on the hyperplane, the last component 0. So it consider that we write down the Bn plus 1 is a unit ball with a metric equal to 4 dy squared over y normal square y normal square y with a power 2. So from this picture, we give the y1 correspondence. Give 1 point of the 0, 0, 0, minus 1. Like from this point, we put one source on this point. We collect to the point on the hyperbolic model P. Then we get the unit point, Q. Q is on the Pangala disk. Use the Y1 correspond P and Q. We can write down the geometry on the hyperbolic model P to the Pangala disk Q. So use this Y1 corresponds. It turns out that the metric, it can be write down ds square. This metric is in fact in the math paper. Let's write down this metric. This metric has the constant negative curvature minus 1. So we have the two models. Then we will can see our result. So for the hyperbolic model, the side for the Horus field is very, very important in our geometry. Horus field is one of the total umbilic hypersurface in hyperbolic space. So Horus field, for Horus field, the Prince curvature is equal to 1 identity. So can be write down this way. HZR, we write down the Horus field, means give one plane. Plane is minus for this vector in the product with Z1 equal to ER. This is hyperplane. Use this hyperplane intersection of the hyperboloid hyperbolic space. We get one, we call it the Horus field. We can check this is the hypersurface in hyperbolic space. Also, all principal curvature equal 1. So, but if use Pangala disk, we can write down picture. So, what is the Horus field? So here is one picture. So we use the Pangala disk. So the Bn plus 1 is Pangala ball. But here we have the Z. Z is belong to the unit field. So in my picture, Z is because Z belong to unit field. So we can draw the Z. Z is one vector on the field. So R, we can draw picture because we have the Horus field. Horus field is one circle, is tangent one point Z. So we can calculation. The R is just the hyperbolic distance from origin to Horus field. So this Horus field, there are two quantity. One is Z. Z can draw picture here. The R is the distance from origin to the Horus field. So in some sense, use the Pangala disk, we can draw the picture Horus field geometrically. So with this concept, we will introduce the concept we call it strictly horosphically convex. Means for simplicity, we write down the strictly H convex. H convex means H is horospherically. That means is the Prince curvature is not less 1. Or we also see the omega, the boundary is smooth. The strictly H convex means Prince curvature is big 1. There are some geometry. Give one boundary on the P is a boundary of omega. What mean? The point P, Prince curvature is big 1. There are some geometry. Past P, we can draw one Horus field. Means past P, we can draw one Horus field. This Horus field is past one point Z. Z is the boundary of the ball. Then the omega, the inside, of the Hall field. So if we think of the Hall field as a hyperplane on the domain Euclidean space, so past P we have the Hall field. Hall field includes the omega. That means that this point P is H convex with geometry. So in my talk we pay attention to H convex concept. Before people pay attention about the convex, convex in some sense is important, but in the theory we will see H convex is more essential. So okay, with some background, we will introduce a new concept. These two concepts is developed by Brunn-Minkowski and Haizhong Li and his co-author in 2021 in Journal European Mathematical Society Journal. So this several line is very important. Give one domain omega on the hyperbolic space. X is one point on the boundary of omega. U is autonormal unit is outward unit normal. Then we can check because X belongs to hyperbolic space. X in a product X is minus 1. U is because outward unit normal. So product U equal 1. But X nu is orthogonal. So we can check X minus nu. This vector X minus nu, this is very important. X minus nu is very important because this vector in Minkowski space, yeah, Minkowski space. But we can check this vector is the length is 0. So people call this vector is light-like. So first thing we should check S minus nu, the length is 0. The second we can check the last component X minus nu is positive. So we can write down X minus nu equal to positive function, positive number. We write E minus U with a Z1. Then from this identity, we can define two concepts. One is Z, the other U. We call Z. Z belong to X minus U is light-like. So the length of Z is equal 1. So Z belongs to unit field. We also can define the U. We call the U the horospheric spot function. That means this spot function is different before to study for the shape surface in hyperbolic space. So two concepts is come out. One is Z. Give one point of X on the boundary omega. We can define the Z. We also use this identity. We can define U. We call the horospheric spot function. These two concepts are essential in our study. So what is geometry? Z, we can see geometry Z is here, because Z belongs to unit sphere. So Z is correspond to Horus field. You can see pass Z, and we can the Horus field. This is the point of the boundary omega. Give the boundary omega, we can because we draw the Horus field, we fix only Z. So this is geometry Z. So but it's geometry U. U is just the distance between the origin to Horus field. So this point origin 0, 0 is the center of the unit ball. So we define two concepts of the geometry. One is Z. Give one point of a boundary of omega. We define the Z. Z is the Gauss map. We call it the horospheric Gauss map. And also we define the U. We call it a horospheric support function. So this identity is very important in your study. Okay, use these two concepts, we can study the H convex hypersurface. So given H uniformly H convex bounded domain, we can define the Gauss map. We call it horospheric Gauss map. We also can define the phi z equal to E uz. Uz, we call it the horospheric support function. Then, given uniformly H convex domain, we can write down the position vector by support function uz. So here, this identity is very important. Means if omega is H convex domain, we can define the horse-fixed spark function UZ. Then we decide that the phi Z. We have phi Z. Phi Z is a function on the sphere, Euler sphere. We can write down the position vector. So this identity can be found as a Brunn-Minkowski and his cause people, and also some other people, but just recently. This formula tells us for the H convex bounded domain, this domain is one corresponds to the one function on the Euler field. This reminds us it is possible to study H convex domain with the analysis of the function on Euler field. So I write down just the right sigma ij is a canonical metric on the Euler field. We define one metric, we call it Aij. Aij is phi ij Haizhong of the function phi minus half normal square d phi of the phi sigma ij plus half phi minus 1 of phi sigma ij. This is the symmetric metric in our theory, play very important role. Means given H convex domain, we have the support function phi. We can write down the position vector. But conversely, how can start for the function on the Euler field? How can define the H convex domain? We find just require this symmetric metric is positive. If this give a function on Euler field, if you require this Aij symmetric tensor is positive, you can get from the construction, you can get the uniform H convex domain. Then they give the one correspondence. So this is very similar to study the convex geometry in Euclidean space. But the complexity is Aij law is some sense complicated. In Euclidean case, there's some similar, the analog of Aij is Kodachi tensor on the Euler sphere. But here, the Aij is symmetric tensor on the Euler sphere, but not Kodachi tensor. Also, we have some relation of the Aij with the second final form of the hypersurface. So Hij minus delta Ij times Aj k phi z equal to 1 over phi z sigma k. Sigma k just mentioned is kinetic metric on the Euler sphere. D mu is the element of the hypersurface of partition omega is equal to determinant A phi z d sigma. D sigma is measured on Euler field. So we also can write down phi z. This is defined by the horoscopic support function, but in the general study for hypersurface in hyperbolic space, we have the U tilde. U tilde we call the support function, means conform vector field product with the U normal. This U tilde is we call the support function. But I just mentioned, now we introduce the horoscopic support function, play some very important role. But there are some relation. Phi z is defined as the Hall support function equal to 1 over cosine r minus U tilde. Cosine r is decided we know it by sin r. Sin r is appear in the metric of the hyperbolic space. So I just mentioned, use this support function, you can do analysis, but you can do convex geometry for hyperbolic space. One concept is we use the horoscopic support function. It's something this is very important, very new. Okay, use this concept. I will introduce our discovery of the hyperbolic summation. Give two domains on hyperbolic space. How can define the summation of two domains? This summation is still one domain. So I think since the Euclidean space, this analog was discovered by Minkowski and Brunn, I think more than 120 years ago. So, but I think it's more than 100 years. For hyperbolic space, people study convex geometry because love this concept. So convex geometry mainly study on the Euclidean space. Use field result for the hyperbolic space. Now I will introduce our main discovery we call the hyperbolic summation. Before that, I will recall what is the Minkowski case for Euclidean case. Euclidean case is simple, yeah, because we recall the pointwise Minkowski summation in Euclidean space. Give K hat, L hat is two domain in Euclidean space. A, B is non-negative real number. We can define A K hat plus B L hat equal to AX plus BY just unit for the every X belong to K hat, every Y belong to L hat. Just a linear combination. This is summation. But what is difficult for the Euclidean case, hyperbolic case, why people more than 120 years, people can find this concept. The reason is people know because in Euclidean case, Ax just By have the linearity. But the hyperbolic space, people cannot know this linearity. So how can we do? We first define the two sets. We want to define give 2 points in hyperbolic space. How can we define the summation? So what is summation of 2 points? Yeah. So okay. Give A is non-negative, B is non-negative to the real number. X we write down X with x1, x2, xn plus 1, xn plus 2. So the first n plus 1 component, I write X. Similarly, I write Y equal to Y n plus 2. The Y means the first n plus 1 component. And W, we can write down W, Wn plus 2. This is 3 points on the hyperbolic space. So suppose W, X, Y, Z satisfy the following inequality. This seems complete, but I will have some geometry. Ax plus 2 plus Bn plus 2 minus W plus 2. So I think this identity is right here. Xn plus 2 plus By plus 2 and Wn plus 2 not less Ax By Ax plus By minus W. Because I write X equal to capital X, okay, capital X, X plus 2, Y equal to Yn plus 2, W equal to Wn plus 2. All this belong to the Hn plus 1. Then satisfy this identity. If X, Y, Z, X, Y, W plus satisfy this identity. So what means this inequality? This equality means Ax, this means Ax, this equality, this means this vector, Ax, By minus W. Inside the function net count of function net count of origin. Okay, this is important. So this inequality, there are some geometry. Yeah? So we want to define give X, give Y, give AB. AB we suppose AB is non-negative. We can define what is the summation of 2 points. So give X, give Y, give real number A non-negative, B non-negative. If satisfied this identity, we call the set. If W satisfied this identity, this inequality, we call the set is Bax By. Bax, By. means equal W. W satisfies this inequality. So give x, y 2 point, give A is non-negative, B non-negative. If they satisfy this identity, this kind of W, we write with this set is Bx, Bax, By. This is set. You can see this set. Okay, I have some geometry. Give Yx is here because I just said x belongs to hyperbolic space. Y is belong to hyperbolic space. How can define the Bax, By? First, we construction T. T is equal to Ax, By. Ax, By, we can draw some picture. Ax, By, for example, we choose AB such that T is inside of the hyperbolic space. Inside, not on hyperbolic space, inside. I will see. This will, if I want T is inside the hyperbolic space, either AB satisfies A plus B, not less 1. So, okay, we have the T, get T. T not hyperbolic space because law linearity. So then we have we write the green shader. Green shader. The green shader is, how can get it? First we get this origin. We collect the T to origin. We get 1 point T prime. T prime is on the hyperbolic space. Because T is inside, collect the T to origin. We get the T prime. T prime is on the hyperbolic space. Then we can check because T is timelike. So log square minus TT is a real number. We use this T prime as center, maybe we can geodesic ball. Geodesic ball's radius is log square minus TT, the geodesic ball. So geodesic ball is red domain, is our geodesic ball. What is summation? Summation, roughly speaking, give x, give y, summation is geodesic ball. 2 point, we get the summation is geodesic ball. Our summation is just make all this kind of geodesic ball, make all the unit of geodesic ball. This is our definition. Point size definition. So I make them a summary. Suppose KL is 2 set in hyperbolic space. Suppose assume A, B non-negative and the real number. We define the point-wise hyperbolic summation KL. Just unit all kind of geodesic ball for arbitrary x, arbitrary y. This is our summation. This is some sense surprise because before the Euclidean case give 2 points, we make summation just 1 point. But the hyperbolic space, because law linearity, they are different. So some sense. So okay, we also can make a remark if this is summation, because in Euclidean domain, people Ferry introduced something like the P sum. So we can do similar. If a P positive, for any real number, we can also introduce the point-wise hyperbolic P summation. And the just I talk correspond to P equal 1. And the hyperbolic summation AX, AK plus BL only depend on the relative position of the KL in hyperbolic space. The last remark, in fact, we first studied this case. I just tell you the point-wise definition, where this definition come from. In fact, we study smooth case. Then we go back, we find the point-wise definition. This is important. In fact, our definition is taken from this property. Give K and L to smooth H-convex bound domain if A non-negative, B non-negative, but A plus B not less 1. Then we can check AK plus BL is smooth H-convex bound domain. Why need A plus B not less 1? In previous picture, A plus B not less 1 guarantee this point T is inside of the ball. If law A plus B not less 1, T can be get out. T is outside of the hyperbolic space. Our definition is empty. not set. You cannot find the T prime. So this is the geometry meaning. Okay. Before I just mention the pointwise definition. Now I will see the hyperbolic summation, not pointwise, for smooth case. In fact, we find that this way. Suppose A, B is two real number, not negative. A plus B not less 1. K-L is smooth uniform H-convex domain in hyperbolic space. Suppose here is definition modular. Suppose KL can be degenerated at one single point. We define the hyperbolic summation omega equal to AK plus BL by H convex bound domain by support function. Means because we give the K is H convex domain, we have the support function. We call the Horsfield support function. L is H convex domain, we have the Horsfield support function. Use the previous two support function, we can define the new support function, U omega. Give U omega, we can write down phi omega, yeah? U omega equal to define the log A EU K plus B EU L Z. So this support function is defined on the unit sphere. We can check corresponding to this function, the metric, symmetric metric I just mentioned, Aij is positive. So means under this condition, especially A plus B not less 1, we can check this support function decided the one domain, H convex domain. So this is for smooth case. Pointwise definition, it doesn't matter smooth or not. So we can check this kind of definition is well defined. Well defined, you means you should check. You define this support function is really corresponding to one H convex domain. We also can check pointwise summation and this for hyperbolic summation. Two concepts are compatible. Means if a domain a smooth case, two definition is coincide. So it means compatible. In fact, in the beginning, we find this kind of definition. Later, we study, we find that we can introduce for the any summation for two sets. Okay, so we will say what the relation. People talk this, give this talk, I think maybe almost 1.5 years. People ask what the relation your summation with the Euclidean summation. Here I just tell you they are coincide. So we can think of the hyperbolic space, not the constant cyclic convention minus 1. We can see the general hyperbolic space with the constant cyclic curvature minus c squared. If c equal 1 is a cyclic curvature minus 1. If c is not 1, means minus c squared. So here we can see geometry. There's some relation of geometry for the hypersurface Euclidean space and geometry of the hyperbolic space. We use this minus c squared. The reason is this is Riemannian manifold with a second curvature minus c squared. If c go to 0, this second curvature will go to 0. So second curvature go to 0 means the limit case Euclidean space. So in this sense, if you get the geometry of the hyperbolic space, hypersurface in hyperbolic space with a minus c squared, you get any theorem. You just make some limit, you get the Euclidean theorem. For example, you prove the Alexandrov theorem with the CMC theorem. For Alexandrov theorem said CMC embedded hypersurface in hyperbolic space is totally umbilic. Let C go to 0, you got the Euclidean result. We call the Alexandrov theorem. The other example, you get the Minkowski formula, series formula. You have the Minkowski formula for the hypersurface in hyperbolic space with a constant factor minus c squared, go to C, let's see this, you got the Alexander function, or you got the Alexander of Minkowski formula for hypersurface in hyperbolic space. Anything. For example, you prove Haizhong inequality for hypersurface in hyperbolic space with a section curvature minus c squared. Go to let's see, go to 0. You also reduce to theorem in for hypersurface in Euclidean space. Even Hopf form, you get one for CMC. You construct one Hopf form for the surface in hyperbolic space minus c squared. You go to 0. You got the hypersurface Hopf form in Euclidean. So many geometry result you can think this way. So in this sense, you can see two-side hypersurface in hyperbolic space is more complicated, more hard than the Euclidean case, because the limit of the result for hypersurface the hyperbolic space will reduce to Euclidean case. Here, the sameness happen. For the simplicity, we can see this is the which you see equal 1. For the dimension equal to n equal 1, we have this is we can say you have two models, yeah. So give x, give y is h2. You got one whole circle, one dimension, high dimension we call whole sphere, but one dimension whole circle. Okay, you get one whole circle. You have the p and p prime on the whole circle. You just fix the p by t, yeah, go to the proportion. So my definition said that give x is hyperbolic space, y is hyperbolic plane, x is hyperbolic plane. We get summation is ball. B is our geodesic ball. So this is our definition. But if we change the C, this give x, give y is a hyperbolic space. You got the summation geodesic ball. But if you change -1 to -1/4, you can see ball will be smaller. If you change smaller again, you change C minus c squared to -1/16. The ball is smaller. When C go to 0, this ball will become 1 point. This is the Euclidean case. So in this case, our definition is coincide with the Brunn and Minkowski summation in 120 years ago. So here, because use the summation, we can develop the theory in the convex geometry. We call it the convex geometry for hyperbolic space. So you just take the book, Schleider's book. Schleider have books from convex geometry for Euclidean space. You have the book. So just look one by one, because before no summation, no theory, you can check every result. See, oh, what is this? What is this? To find. No, I just mentioned some important results here. So because we have sum, we can introduce a measure. Before no summation, you cannot introduce measure. So first I introduce a measure. By introduce measures, we find the concept, introduce the Banyos and his course is very important. Before in Santalos book for hypersurface in hyperbolic space, there are some core mass integral. But for our concept to find our theory, we find the core mass integral not important, and the modified core mass integral is more important. Okay, this is the quality. W0 tilde is volume. W1 tilde is not area, is combination area and the volume. Yeah, so on. We can define the WK plus 1 tilde, a combination with the WK tilde with the integral of the PK K tilde. K tilde is shifted principal curvature. Principal curvature the K1, K2, K shifted principal curvature kappa 1 minus 1, kappa 2 minus 1, and kappa n minus 1. When shifted principal curvature important in our theory, because we introduce the concept we have the symmetric tensor Aij. Aij have a relation with the kappa I minus 1, not kappa I directly. Okay, use this modified convex integral. We in Brunn-Minkowski and the Haizhong and the course paper, they make some variation. They can calculation if the we make the form of the domain with the speed function is very f, then the derivative w k tilde equal to integral f times p k tilde. So use this, we can see, we can introduce with my former student Botong Xu. Now he doing his postdoc in Israel with the Myanmar. Okay, we can because we have the summation. We can summation for p summation. We can define. We can define introduce the measure. Okay, this is following the concept. We call it p mixes case modified convex integral for two smooth H convex domain KL. Give two domain KL H convex. We can define the WK WP comma K tilde. Just use some limit, limit. Because we have some summation, you can make the limit. No summation, you cannot calculate. But very funny. Here why use here is p belong to half and 2. This is some subtle, because according to smooth case, we just can define the p from half to 2. Is different from Euclidean case. Okay, I don't give detail here. Use this, we can calculation. Okay, give two H common domain K and L. We can define this limit. And then we find the integral on the right hand side involve FL. FL consider support Horsfield support function of the L. Phi K is if you consider Horsfield support function of the K. Also, okay, you can define A, the symmetric metric. Okay, similar to Luttwak did in 1993, you can propose the Horsfield case P area measure. Just use the yellow term, yeah. So okay, we introduce the measure on the domain. We can propose the P because the problem. Because we distinct for the Euclidean case, we write the Horsfield P because the problem. Then the equation is also related to Monge-Ampere type equation. So in smooth case said phi minus p z pn a phi z equal to fz, means give a function f on smooth function on the domain, a smooth function on the unit field. How can you find the convex H convex domain? That means to solve this equation for the phi. So you can solve the equation phi, satisfy the metric is positive, means you get the H convex domain. So this is the Minkowski problem in hyperbolic space setting. Before people just study the Euclidean case because nobody can introduce summation, no measure. You can study, but no geometry. You don't want to study. Okay. The Euclidean cases there are many studied. I just mentioned. For example, Luttwak introduced the P because the problem in different geometry in 1993, and Zhou and Xu Jiawang and some other, and for general case, P equal 1 is a classic Minkowski problem. Was studied the Minkowski, Alexandrov, Fenchen, Levy, Yunenberg, Shaoyuan Zheng, and Yao, Poglev, and Kaveri, so on. But the hyperbolic city show the set is this equation. This I just mentioned. Okay, we also can propose to study the Horsfield P Clover Minkowski problem. Means just solve this equation. Phi minus P minus K, Pn minus K equal to phi z, equal Fz. Means give a smooth function, positive function Fz. How can you solve this equation? Pn minus K means n minus K elementary function of the Brunn curvature. Okay, this equation in Euclidean case also equation become two u 1 minus p pn minus k uij plus u sigma ij fz. This is the Euclidean case and studied by several also. So then there are some also so I can write down equation here, yeah, this equation. So is a special case. P equal to minus n. People call it a Minkowski problem, and the P equal to minus n, we call it the Minkowski problem, and so on. So by use we also find some abstraction for the P equal to minus n. Means if satisfied this equation, we find some identity, some abstraction. Means if f is satisfied this equation, it must set this identity phi minus n df with dxi integral 0. This identity must satisfy. If not satisfied this identity, this equation no solution. So this identity is similar to in Riemann geometry, people call it the Casanova identity, related to conform geometry. The conform metric, the color curvature is given function unit field, and so on. So I don't give detail. So we also can prove some Euclidean result. Give function is constant, we can prove some Euclidean result. So the main result in this section, I and Botong Xu can prove some existence. Give P is any number, can be minus is finite number, real number. We can solve the equation. We can prove there's a following equation. And this is the P Minkowski problem is always solvable. Means give function fz, we always can solve, get a solution of this equation for the gamma. So okay, for the whole figure P Minkowski problem, we also can prove some existence. But in this case, they need some convexity for the given function. For simplicity in our paper, we write hz equal to f minus n minus k, 1 over minus k. F is positive function on the unit field. Need some constriction on the f and the h. So okay, the result can see this way. For if p not less minus n, then give a suppose even function f means function on the unit field f minus z equal to fz. This means even. Then satisfy the above assumption, we can prove the following equation always have a solution. What method we proved? I just give one slide to explain. So we use a curvature flow. Consider the volume preserved curvature flow. We design this kind of flow. This flow seems complicated, but you just see last term. Lambda tilde is the one of the shift Brunn curvature. So you just see this last term. This is for Brunn curvature, is degree 1. There's a minus. So this is degree 1 is shrink type, shrink. So with a constriction here. So this is first is shrinking, is curvature with a minus, with a 1 by minus sign. So is with a constriction here, yeah. So this is a constricted flow. So okay, we design this flow. We want to prove that this flow there's some long-term existence. Then we can prove that when the t go to infinity, we get one solution of the equation we studied. So we design this flow. We show the require some property. For example, first time we will this flow or flow we preserve the modified for mass integral, means the derivative w k tilde equal 0. We also design this, people call it entropy. we call the JP omega. JP omega, we can prove there's some volatility. So means the derivative JP omega t not positive. So I don't give detail, but to prove this kind of flow non-distance existence, we use the Maxim principle and use some technique developed by Andrew and our works before. So now I will just mention something of the discrete case. Because the convex geometry, there are two parts. One is discrete geometry, the other is smooth case. The discrete case means study polynomial, triangle, and some geometry. So here we also propose, so this I think maybe the first paper to study this geometry. So we propose to study H convex domain. Means we propose to study H convex polytopic. So means what it means? This is this Euclidean case. We set a triangle. Every side line is just a straight line. But here we propose our geometry is unit ball. Every side is a whole circle. Not study geodesic line. We study whole circle. So to use the whole circle to instead of the geodesic line is our proposal. Why? Because smooth case tell us something. Okay, use this idea, we can define why H convex polytopic means you have some Horus field. You use some Horus field. You make some intersection. Horus field. Euclidean case use half plane, but here we use Horus field instead of half plane. Okay, we can introduce the H convex polytopic. Use the Horus field instead of the geodesic plane. So use this concept, we can define some concept of the, we call the discrete horospheric P surface area measure. So similar, yeah. Because this is the side is horizontal, give one normal, yeah, you go normal, we can define the discrete version. So this is joint work with from two students. One is Yao Wan and Botong Xu. The concept is developed by with the smooth case Botong Xu. So the other student join us. So we finish. We have the discrete case. We also can define some discrete measure. Also, we can prove some theorem. In discrete case, give one real number. If suppose the measure is even, then we can prove exist original symmetry H convex polytopic satisfy that the measure is proper to given polytopic, something like that. I don't give detail. So the next few minutes, I will see some geometry inequality. So why we can develop this area of this concept and develop the convex geometry hypothesis. The reason because last 11 years I studied geometry flow. Geometry flow tell us something about the inequality. Because in people work on convex geometry, they get some inequality. But because that time maybe no machine. So that's their inequality is not sharp. But use the geometry flow, we can prove some very sharp inequality for the H convex domain or the hyperbolic space. Now I will see what relation the previous result and our theory. So in hyperbolic space, you need some function. You cannot write down some function independently. For example, this function is very important, hk. You defined by for calculation the shifted coordinate integral for the geodesic ball, geodesic radius r. So IKR is one variable function, is have the monotonicity, means the derivative of the IK is positive. So use this we make some conjecture 2 years ago in our theory. So I just see the my conjecture. Give A, B not negative number, and A plus B not less 1. KL is 2 H convex domain. Give we have a summation. Yeah, omega is A K plus BL. We propose exponential I K inverse omega K tilde omega not less A exponential I K inverse W K tilde K plus B exponential I K inverse W K L tilde. We call this is Brunn-Minkowski inequality. This inequality must write down by this function, model function. So is we in our paper we just prove this conjecture for the special case. For example, K equal N, we can prove it. If KL above, we can prove it. So because in convex geometry in Euclidean space, Brunn-Minkowski inequality, there are many kind of proof very important rule. Why? Because Brunn-Minkowski inequality imply the Alexander function inequality, imply the experimental inequality. So in convex geometry, is the Brunn-Minkowski inequality very important. But here we prove this, we propose this. So what's related with the Euclidean case? Similarly, if we change the Abel space, not a constant segregation minus 1, change it to constant segregation minus c squared. If c go to 0, this inequality will become the Euclidean Brunn-Minkowski inequality. So I just mentioned maybe 1 minute, I will say what the relation or inequality. If the conjunction true, we can get the Alexander function inequality. This Alexander function inequality is proved by the Brunn-Minkowski Yung Wei and his cause. I use some curvature flow and many advanced machine. I just mentioned define this function we call the modified case mean radius. Just write that one. If conjunction true, this Alexander function inequality proved by Brunn-Minkowski Yung Wei. Just get from the derivative, because if we have the Brunn-Minkowski inequality, just a derivative this inequality is in special case choose A equal 1, B equal T, K equal L. So that means our Brunn-Minkowski policy should be very hard to prove. This is our work we wanted to continue to prove the Brunn-Minkowski quality. Also, I think I stop here. Thank you for your attention.
We thank Professor Li for giving such an inspiring talk. Are there any questions? And I have a question. So for this theorem by Andrew Chen Wei, so it seems to be a first order consequence of your conjecture. If the conjecture is true, then it follows from this derivative.
Yeah.
Is there a second order consequence?
Yeah.
Like what's the second order derivative?
So is the Professor Bill's question very deep question. Yeah. Because this is make a second derivative. The reason is that for t equals 0, two sides is same. Then you make the derivative is something useful. But if the second derivative is if you want it useful, you should know the for t equals 0, the first derivative same.
Okay. I have another question. So so the hyperbolic sum is right. So in your geometric inequality, you mentioned the interesting conjecture regarding hyperbolic sum. Now, if it's only for the prescribed measure problem, so is the hyperbolic sum used to define that core mass integral only? So So if for the prescribed matter problem alone, does one need to know the concept of hyperbolic sum? For the prescribed matter problem.
For prescribed matter problem, here is just write down to the ample type inequality.
Right.
If you use sum here, maybe is here you can see just depend on one.
Right.
Is the reduced to the equation on sphere.
Right.
Unit sphere.
Right. Yeah. Yeah. I found the hyperbolic sum is very interesting, and I want to know for this problem, does one have to use this concept of hyperbolic sum for this prescribed? Oh, no, right? Okay.
Because use the concept to introduce the magic.
Okay.
The concept.
All
because
right.
if people start this question, but where this question come from?
Okay.
Then because the magic is introduced by our summation. To study this is really analysis on the sphere.
Then in the geometric inequality part, you gave quite a few very inspiring the conjecture based on the hyperbolic sum.
Yeah.
Okay, I see.
Yeah, I think because Euclidean case, you know that there are some deletion. There are some translation. But in hyperbolic space, no translation, no deletion. But we introduce some deletion. But the deletion is not as simple as the Euclidean case. Deletion is just say from the whole sphere support function. We define if a support function, there are some up to some constant we define the deletion. Euclidean case is simple, yeah. Support function deletion is equivalent to the geometry deletion. So some sense hyperbolic space is more complicated.
Yeah. There is another related question. So for the descript problem, you mentioned the descript problem. What's the analog in the Euclidean case?
You are good question. But that's the first thing. There are some distance. For example, in Euclidean case, you have the triangle, yeah. But in hyperbolic space, the hyperbolic space, there something like this. That, for example, this is one side, this other side. You know? We have this polynomial, just a triangle. This so there are some relation. The relations we use similar. We use this geometry to see. So, for example, we must see this. Right? See, go to zero, something like this. You consider the discrete version in hyperbolic plane with a second curvature minus c squared. If c zeta, if c go to zero, you got the Euclidean analog. So show to this.
So are these Euclidean analog? No. So what's the name of those of such a result in the Euclidean case?
In Euclidean case is you will see because here is I draw picture in this. Yeah. I draw picture in this. Yeah. If it give some picture this. Line.
Okay.
You get one line.
Yeah. Oh. Okay. Are there other questions? Or if not, let's thank Professor Li again for such a beautiful talk.
Okay, thank you.